Okay, everybody? How's everybody doing? Good. Everybody's got a working robot now? We had a few heating problems, a couple of failures. The build quality on the robotics kit is not the world's best. So sometimes parts fall off. The build quality on the Beaglebone Blue is pretty good. Okay, we are on week 4 of the course, and the goal this week is to develop an URDEF for your robot and to write C code, which is a robot which is, publishes joint states and publishes a transform TF for the base of the robot. And we looked at that last time. We'll briefly review it today. Any questions before we get started? We're going to have a short formal presentation, and then we'll have a clinic so you can just work on your stuff, and I'll wander around and ask questions. I keep on saying that, and it keeps on taking longer, but I think it's really true today. Hang on a second. We get some audio going here.
With the immediate goal of surviving in the corridor.
So you may or may not be aware of the fact that robotics has quite a long history at Hopkins. In particular, the Applied Physics Laboratory, which is one of our divisions. It's located in Laurel, Maryland, and they do a lot of work for NASA. They developed 2 of the recent planetary probes, Messenger and New Horizons, one that went to Mercury and one that went hurtling past Pluto. Those were developed and operated from the Applied Physics Lab down in Laurel. There's about 4,000 employees there, and they do a lot of defense contracting, defense work for the DoD, and build a lot of satellites. Very sophisticated group, and they early in the 1960s they had an internal research and development project to develop a robot called the Hopkins Beast, and fortunately some video survives of this, and so I thought I'd share that with you as the robot of the week.
Mobile automaton tested. This Mod 2 mobile automaton was designed by APL's Adaptive Machines Group with the immediate goal of surviving in the corridors of the Applied Physics Laboratory. It weighs 100 pounds, and into its 19-inch diameter are packed 150 digital logic circuits, batteries, servo loops, and drive motors connected to 2 of the automaton's 4 wheels. The automaton survives by feeding or charging its batteries at wall plugs. Micro-switch sensors position the automaton's head so that 2 prongs can be inserted into the plug receptacle.
Notice no ground pin. This is back in the day.
This console can control and monitor automaton activities. 21 different operational modes, including sleep, feed, free, vibratory, and high and low speed are possible. Information is exchanged over an RF link. The automaton has been turned on, and sensing that its batteries are low, searches for a plug so it can feed. It feeds until its batteries are charged above a preset threshold level. The automaton has in fact 2 goals: to keep moving and to survive. Having just fed, it will keep moving without seeking a wall plug until its battery charge falls below the threshold value. Since the automaton must feed 4 minutes for every 1 it is free, the value is set to give the automaton a 6-minute free period. It can move 3 hours before its batteries run down. The automaton doesn't learn from its environment, but its circuitry enables it to react in an optimum way to environmental problems. Should the automaton become trapped by obstacles, it automatically shifts to a vibratory mode, during which it radically alters its movement pattern in an effort to escape. Here, the automaton in the free mode passes by a wall plug. Although the automaton is not learning from its environment, its designers are learning from the automaton. They are finding ways to impose sophisticated behavior patterns on electronic circuitry that controls mechanical systems. The techniques being learned with this automaton may prove useful in designing machines to operate in remote areas such as the bottom of the sea and planet surfaces. The Mod 2 mobile automaton is still under development. To its single probing arm are to be added ears and an eye. This circuit board is part of an acoustical system operating at 40 kilocycles that will enable the automaton to maneuver down the corridor without touching the walls. In operation, the system will transmit 2 side beams, measure return time of reflected energy like a radar, then turn the data into middle-of-the-road steering commands. The optical system will locate and identify wall plugs. Its half-inch Vidicon unit is designed to recognize rectangular objects with a height-to-width ratio of 1.6 to 1, the aspect ratio of the cover plate of a wall plug. As the automaton moves down the corridor, the eye looks out 45 degrees to the right toward the wall. When it sees some object, the optical system moves the automaton in for a closer look. Upon recognizing a cover plate, the system guides the automaton to the plug for feeding.
So APL has been doing great things for a long time, and I thought you might enjoy that. Any questions before we get going? All right, just a couple things that I wanted to mention. One is homework 2 is graded, and I'll be posting grades shortly. The only problems that people had on number 2 were several students submitted code that read parameters, but their launch files didn't actually set the parameters. And so the TAs now were guessing that maybe you were setting the parameters by hand in the command line, and we wanted you to set parameters in the launch file. And the second one was some students' code used standard output to print the value of parameters out to the screen, and which is fine, but then you couldn't actually see them on the screen because by default, for example, here's a ROS launch file. By default, the standard output from a ROS node goes to dev null. It is lost entirely, and so it doesn't. Otherwise, you'd have tons and tons of stuff streaming up on your screen because you'd be launching 10 processes, and then I'll be writing all sorts of stuff to the output. If you want to have the output for a particular node go to the screen, then you need to add an additional argument here, which is minus minus. So if I wanted the here's the name of my program, and if I wanted printf statements and things like that to appear on the screen, you need to add minus minus output equals screen, and that tells ROS launch when you run the program to connect the standard output of that particular node to the terminal. And you can have more than one that are connected to the terminal, but generally you don't want to have too many things streaming out to the terminal, or it can just get confusing. So if you're wondering why your printf statements didn't appear on the screen, that's why. And this week's assignment, got it here. One problem that I noticed early this week as students were handing in assignment number 3, that I just want to mention because several students were having difficulty. Right here, I've updated the web page a little bit. So there was a tutorial that you did which explained how to do how to program ROS when you have multiple machines, and on each machine you need to set a ROS master URI and a ROS IP. And so some of the problems that people were having was that so this ROS master URI needs to be the IP address where ROS core is running, and by default we use the TCP port 11311. That can be different just as long as all parties agree to a different port. ROS IP is the name of this PC, the one that's actually running the code. And two things that that I observe people are having trouble with. One is some people, this recommends that you edit these lines into your bash RC. So you know that in your root directory, .bashrc is the file that gets run every time you open up a new shell, and it initializes the environment variables. And so several students were typing these commands in by hand, and that's just painful. And so at the tail end of your bash RC file, you should have source opros kinetic setup.bash. You should source the devel setup.bash for your local workspace, and you should set these environment variables right here. And that way, whenever you create a new shell, they'll automatically be initialized. And remember that when you edit this bash RC file, it doesn't retroactively automatically change the environment variables in your current shell. If you want to, so if I edited these things to a different value, then it doesn't automatically update the values in this shell. In order to update the values in this cell, I need to type source.bashrc. And then I can check by typing printenv and then grepping for ROS, and I can verify that things are set properly. And so you really don't want to be typing these things by hand each time. And I'm going to post a Google spreadsheet shortly. And when you're in class, using that router, I can reserve you an IP address for your robot and reserve an IP address for your computer. And what I need you to send me, or you can put into that Google Doc when I post it, is just ifconfig, so for your PC and for your robot, this is the wireless Ethernet adapter, and this is the IP address in the local network. This is the .10 network. And the hardware address, this is what's the so-called MAC address right here, the hardware address. And so if you want to have a reserved IP address for your robot and for your PC, so you don't have to be editing your bash RC all the time while you're in class, I need you to send me those numbers for your PC and for your robot. And the last problem that some people were having is they were getting confused between ROS master URI. The ROS master URI specifies a universal resource indicator, so it's HTTP and then blah. And the ROS IP is just an IP address. There's no HTTP. So some students were, if you put an HTTP here, then you'll get an error saying that it doesn't know what to do with that. So one's just an IP address and one is a full URL. On this week's assignment, I think we covered everything pretty much yesterday. Do work through these tutorials. If you do these tutorials, then the assignment is very easy. If you don't do the tutorials, then the assignment will be very hard. You can skip, if you want, the parse rdef file and start using the KDL parser. So 2 and 4 of the second part you can skip if you want. They won't take you too long if you want to do them. And recall that, and I've updated this plot here. So this is you're going to extend the package that you built last time. The package you built last time had a joy node and a joy twist node and edumip ROS balance. And what you're going to add here is a robot state publisher that subscribes to the edumip state. And we saw that last time when the robot is running ROS topic echo edumip state. So those are the state messages being published at 5 hertz. And you can have, and it publishes a body frame easting and northing and a body frame heading. So it's in units of meters and radians. And if you look at the message file for edumip messages, so if we look in ROS Catkin workspace, source, you're going to have to install this package, edumip messages, and it's a package that we've made for you that you can just git clone. Edumip messages has one, it does one thing, it defines the message edumip state. So there it is in the message directory. And you can look at that message definition file, and it will decode in the comments what all the fields are. And in particular, the displacement, and this is the commanded body tilt. Theta is the actual body tilt, so that's one that you want. So the commanded body tilt and the actual body tilt. And you also want the heading and easting and northing. And And I'm going to update this. I thought I had the Git repository for this message listed here, and I'm realizing that I didn't list the Git repository, so I will list that Git repository, and you can just pull down the package. So that's the message definition in edumip message, and so I've asked you to make a C file that subscribes to this message. It publishes joint states, and it also publishes a TF for the base of the robot. And the joint states are read by the robot state publisher, and they publish the TF for the two wheels on the robot. And my launch file, when I did this one, looked like this. So I'm launching a joy node. I'm launching a joy twist node. This reads the joystick, publishes the joystick message. This reads the joystick message, publishes the twist. This is the C++ node that I wrote, which subscribes to the edumip state messages and publishes a TF for the base of the robot, and it publishes the joint states. And this is a system-defined node called Robot State Publisher in the Robot State Publisher package. And it subscribes to /joint states, and it publishes the TFs of the wheels. Your program needs to publish the TF of the base of the robot. And then this is how we're loading up the robot description from a Zacro file. I chose to make a Zacro file. And then last but not least, this launches RViz with the initialization file for RViz. And so if I look here in ROS Catkin workspace, source, edumip my robot, or maybe it's easier if I do this. So we're in ROS Catkin workspace source edumip my robot. This is the package. So your package needs to have a cmakelist.txt and package.xml. It should have an rdif, which is where your rdif file is for the robot. And it should have a source directory, which is where your a source directory, which is where your C node is, an RViz directory, which is where your RViz initialization directory is, file is, and then a launch file, which contains the launch file. And recall that the rdif so I chose to use a Zacro file rather than rdif, and the reason that I chose to use Zacro is that I could define things like wheel separation and wheel radius as properties and use them and do math on them to make it easier to define the different things. And you're doing a tutorial on Zacro, you just need to include this language when in the robot name statement. And the RViz file we created by just running RViz and populating it with the different display things and then saving the RViz file in this directory. And the source file in my case, I just subscribe to the joint states with a, subscribe to the edumip state topic with this callback function and set up a joint state publisher that can publish the topics, publish the joint states. And so every time I get an edumip message, I create a transform for the base of the robot, setting up the origin and the orientation, and then publishing this in TF with it. You can see it wrapping around, and it's publishing this transform, timestamp now, and it's the transform from world to edumip body. And then we need to populate a joint state message and publish that in the joint states. And that's it for handling that callback. And when all that works, we're balancing over here, then I should be able to run a so I'm going to ROS launch edumip my robot, edumip my robot.launch. Yeah, it crashed. Try that again. Okay. So that's on my edumip. That looks okay. I'm going to kill it though. I'm going to restart everything. Okay. Now, so RViz came up, but notice the robot's not being displayed. Before RViz will display a robot, it needs to have the base transformation of the robot. Remember, the robot is all reference to the base transformation, and that base transformation hasn't actually been published because my edumip hasn't published any robot state messages, and so my C code hasn't published the transform for the base. And so when you run your program and the RViz doesn't display, that means it doesn't have a full set of transformations. It won't display a part unless it has a transform for the part. And by default, in the meantime, the part will hang out at 0, 0, 0. So, and it won't have any color. So when you see the white ghost, that means that you have not all your transforms are being published. And indeed, if we look at our ROS topic, echo/tf, there's nothing there. Nothing there because the robot hasn't published any states. The robot doesn't publish any states, then our C code doesn't publish any TFs. And so if we log into the robot, and we run robot code, and so that's the sensors, the code that's processing the sensors. They have some low-pass filters, and so that's initializing the sensors, and it realizes the robot's on its back. And now if I go over here and I sorry, display. So the robot wakes up, and its dead reckoning assumes that it's pointing north when it wakes up, and then it just does odometry, and you can drive around and turn, and notice that Ross topic list. We've got joint states being published, and we have TFs. We can echo the joint states. There they are, joint left and joint right, angles and radians. And we can echo TF. And our code is publishing the transform from world to edge emit body. We saw that. And the robot state publisher is reading the joint messages. It's publishing these two, and is using the RDF to do that. And Ross param list robot. These are the parameters, and robot description is one of the parameters, and we can say Ross param get. And so that's sort of a not very nicely formatted version of the RDF that's generated from the Zacro file. So that's the whole thing. Questions? All right, go for it. So this is the rest of this class is an informal clinic class. You're welcome to hack. If you need to take off, you can, but I'm going to stick around so that if people have questions, then I can work with you on them. So think of it as a extended opportunity to hack and combine with office hours. Thanks, everybody.